So I found the mistake. Right? So I had this number wrong. I guess I missed a number in my calculator. And so this is the crossed out and written in kind of this pink color here, the correct number. And this is the correct number then of this plus that. And so this ratio, this 156,360 divided by 521.1, T2 is about 300 even Kelvin. And that makes a lot more sense. Right? I would expect my temperature to be somewhere between 353 and 298 Kelvin. Right? Or somewhere between 25, the original 80 and 25 degrees C. So I'm getting 27 degrees C, and that's expected. That's kind of where we would expect that value. So that's the reason I was like, wait a minute, I'm getting like 16. That doesn't make sense. Okay, here we are. This makes sense. All right, and that happens, guys. That's okay. That's a small, minor math error, but knowing that the original equation was set up all the way back here, the fundamental first law was correct. There's no way I can get to this point and make a simple math error if this is wrong. Right? So this is the most important part. This is important getting this right, but this we can iron that out. That takes time. Okay, and that's okay. All right, are we done? No. The problem also asked us to find the entropy change. We want to find the entropy change for what's occurring here. All right. Well, so what we really want to do is we want to find the total entropy change, which is going to equal, and a delta S, of course, is going to equal this integral of Q over T plus the amount of entropy generated. Well, here's what we know. This system's not exchanging heat with the surroundings. What's happening is the copper is exchanging heat with the water. But the system itself, if we call this tank here to be our system, it's not actually exchanging heat with everything outside of it. So what's happening is the total change of entropy inside the system is really just the amount of entropy being generated. And that's really what we're going to try to find. So we need to try to find the total entropy change. And what's going on there is I've got an entropy change for my copper and an entropy change for my water. Okay, so the entropy generated is going to equal these two quantities. We can use Gibbs Equation now to find those. So the entropy generated, which is going to be the total entropy change, is going to equal the entropy change for the copper. Well, that's going to be the mass of the copper times, and we said back over here, right? We said if I've got solid or liquid, change in entropy for that substance per unit mass is equal to the specific heat times the natural log times the change in temperatures. Make sure you use absolute temperatures there, Kelvin or Rankine. Well, I need to know the total big S, so I'm just going to multiply by Fm to get there. So mass times little s2 minus little s1 for the copper, plus mass of the water times little s2 minus little s1 for the water. And again, we can use Gibbs Equation to find that. So that's mass of the copper times specific heat for the copper, which we've now agreed upon a value, times the natural log of T2 over T1 for the copper, plus the mass of the water times specific heat of the water times the natural log of T2 over T1 for the water. Okay, so you can plug in your values here. I'm comfortable I can just pull them off because they're all up here, right? Or I can go back to my givens and find them. So let's just see if we can run these through the equation real quick. So the mass of the copper we said was 50 kilograms, right here, right? 50 kilograms. 50 kilograms, and actually I'm going to do the natural log first. I'm going to do this guy first. So I'm going to say T2 for the copper we said was 300 divided by the initial temperature for the copper we said was 353. I'm going to take the natural log of that quantity, and I'm going to multiply by the specific heat of the copper, that's 0.39, and I'm going to multiply by the mass of the copper, that's 50. So this is this quantity times this quantity times this quantity. Now notice I get a negative quantity here. This is minus 3.17. Now, before we talk about that quantity there, let's look at the units. I've taken 50 kilograms times 0.39 kilojoules per kilogram Kelvin. So 50 times 0.39 is kilograms times kilojoules per kilogram Kelvin. And this is unitless. So that leaves me here with kilojoules per Kelvin, be my leftover units. Okay? Now again, we said that's negative. Why is that negative? Does that make sense? Well, think about it. What's happening to the copper? It's cooling down, right? The copper is cooling down, meaning the molecules are becoming less chaotic. They're becoming lower entropy. So I should expect when a substance cools down, I should expect a decrease in entropy. Now, a lot of people will say, wait, Steve, you said entropy generated can't be negative. That's right. But this isn't the only entropy term. There's this one too. So let's talk about this one. So add to it this guy. Well, again, the mass of the water is going to be, well, before we do the mass, let's do this guy. Let's do the natural log. The water is going to go to, the final temperature of the water is 300. It's starting out, we said, at 298. Right? And then take the natural log of that ratio. And then multiply that by the specific heat of the water, we said was 4.18 kilojoules per kilogram Kelvin. And multiply by the mass of the water is 120. So that is the entropy increase for the water, a positive 3.355 kilojoules per Kelvin. And so I'm just going to subtract from that this 3.17, the entropy loss by the copper. So the total entropy generated is going to be 0.185 kilojoules per Kelvin. And that just tells us this is an irreversible process. Once this has occurred, we can't go back to the initial state without leaving a mark on the system or the surroundings. And that's the second law of Thermodynamics. All right, how are we on time? Oh, good. We can at least start into the next problem. Okay. I think I've got answers here. How do we do? Yeah, actually, we're pretty good. I do have answers. T2, they said, was about 300 Kelvin, and the entropy generated was about 0.2 kilojoules per, and it should be Kelvin. Those units are wrong. Shame on me. Kilojoules per Kelvin. Okay? Awesome. So far, so good. Let's keep going, shall we? So, no ink. Next slide. All right, now this is not 797. It might have been 797 in the 6th edition. We're in the 9th edition. But the problem is just fine, okay? So, this problem, we can work this problem a couple of ways, and we'll see how far we get today. We've got air entering an adiabatic nozzle. We're given pressure at the inlet and outlet. We're given temperature at the inlet and speed at the inlet. And assuming variable specific heats and assuming reversible, they want us to determine the x velocity. And this is what I would suggest to you. I said earlier we might work this one two ways. Let's not assume variable specific heats initially. Let's assume constant specific heats to begin with. That's what we just did here, is we assume constant specific heats to solve this problem. Let's assume constant specific heats, talk about how this problem works, and then we can go back and talk about how do we use variable specific heats after we look at this one with constant specific heats. Okay? All right. So we want to determine the exit velocity. Well, what are some good tools we would have to find an unknown speed or exit velocity? That's right. At this point, a gag reflex is anytime I'm looking for an energy or something to do with energy, the first law is normally a good first guess. It's something I can use to try to find an unknown quantity. So let's organize our problem here. What do we know? We know givens. I know inlet pressure, 60 psi. I know exit pressure, 12 psi. I know an inlet temperature, 540 degrees Fahrenheit. That's really hot. Really high temperature air. Initial inlet speed is 200 feet per second. That's really fast. if this is in a jet engine or what this is, but that's okay. They've told us that we can assume that it's reversible, and they've also told us it's adiabatic. So there's always those things that aren't numbers that they've told us. They've told us Q is 0. They've told us it's adiabatic. They've also mentioned that it's reversible. They might say determine the maximum exit velocity, or they may just simply tell you, you know what, it's reversible, which tells you that it's not generating entropy. This is the best case scenario. They want us to find V2, the speed at the exit. And again, we just have a nozzle. Mass and mass, and they have told us that this is air. Just good old-fashioned breathing air. So we've got mass in and mass out. And again, how do we find an unknown speed? Well, the speed is linked to the kinetic energy. I might be able to find the kinetic energy through the first law. And so we set up the first law and say, what crosses the boundary? Well, I've got mass, E dot mass in, minus E dot mass out. Is there heat? No. It's adiabatic. Right, so the other things that can cross the boundary, of course, are heat and power, or work. I've got mass. I do not have heat that's given, and I don't see anything applying power. There's no electricity. There's nothing extracting work. That's it. And that's equal to the change. So in minus out equals the change. It's a steady flow control volume, so we're going to say that the change is 0. So I've got a single inlet and a single outlet, so it's a single m dot. I know I'm going to have an enthalpy change, so it's H1 minus H2. And because it's a nozzle, I also have a kinetic energy change. So this is plus V1 squared minus V2 squared, both over 2. And that's equal to 0. All right. So we start saying, okay, what do we know, and what can we find? We're looking for V2. So that means if this is the only equation I've got, I need to be able to solve V2. That needs to be the only unknown I've got. Well, I do know V1. I do know this is an ideal gas. This is air. The H values, both the H and the U's, are functions of temperature. So if I know the temperature, I know the H values. I do know the inlet temperature. So I do know the inlet H, or I can find it. I do not know the exit temperature. Therefore, I do not know the exit H. So now I've got two unknowns here. V2 and H2, I do not know. I do not know m dot. Right? I don't know m dot, it's not given. I don't know the areas on this thing. So you don't know the areas. So if I knew the areas, I do know I could find the specific volume at the inlet using ideal gas law, or at least approximate it. So I could find m dot if I knew the inlet area. I do not. I don't know the inlet area. So, yeesh, I've got three unknowns here. Well, one of them you can kind of get rid of. Notice what happens if I divide both sides of this equation by m dot. Right? Take this, divide both sides by m dot, and I get 0 divided by m dot, which, assuming m dot is non-zero, and m dot is non-zero, that's a safe assumption for us. The mathematicians would cringe at this, but no, this is okay for us. Mass flow rate's not going to be 0 in this case, so this is okay. So I can just work this problem per unit mass. I don't have to worry about the m dot. If there was a certain amount of heat transfer, if it was not 0, or if I had power input of some kind, this fancy trick doesn't work. But since everything's multiplied by m dot, I can just divide it by it, and it goes away. So that's one unknown I don't know. That I don't care. I'm still trying to find V2. That's what I'm looking for. I don't know H2 because I don't know T2. So I'm going to need something else. Okay? So I can only solve for one unknown here. And that's where we're going to pick up the next video, is what are we going to use to find H2, so I can use this to find V2. Loud pop.